Okay, let's dive right into one of the absolute most mysterious and fascinating phenomena in the entire universe. Welcome to The Explainer, where we take these massive, complex concepts and just break them right down. Today we're looking at black holes, and specifically how pop culture gets them incredibly right, but also terrifyingly wrong.
You probably remembered the climax of that incredible 2014 blockbuster Interstellar. Our main guy, Cooper, falls straight into the supermassive black hole Gargantua. It's a completely wild ride, right? His ship gets battered by these grain-like particles, catches fire from the insane friction, and he has to eject. And then, out of nowhere, he finds himself inside a five-dimensional tesseract, basically using gravity to talk to his past self. I mean, it is amazing cinema.
But it definitely creates a really fascinating mystery for us to explore today. What actually happens when you cross that threshold? Is there really a mind-bending five-dimensional tesseract just waiting in there for us? Or is the actual scientific reality much, much harsher?
To answer that, let's look at Section 1, Einstein and Space-Time.
To really get this, we've got to go back to Albert Einstein, who gave us two absolute game changers. First up, the special theory in 1905, which basically showed that traveling at extremely high speeds actually slows down time. Crazy, right? But then, 10 years later, his general theory showed that intense gravity slows down time too. Interstellar actually nailed this on the Aqua planet, where the immense gravitational pull of the black hole meant that just 1 hour on the planet's surface was literally equal to 7 years back on Earth.
And that time dilation perfectly illustrates Einstein's core concept of the space-time fabric. Think of it like a giant cosmic mesh. When a super heavy planetary object sits on it, the mesh bends. And that bend, that's gravity. What's so profound to me here is that gravity is so powerful, it isn't just pulling physical objects down a slope. It's warping heat, it's warping sound, and it's literally bending light itself, all while causing that massive time dilation.
Now, here's a completely mind-blowing little detail hidden inside Einstein's theory. Gravity actually has a speed limit, and it perfectly matches the speed of light. So gravity isn't just felt instantly everywhere across the universe all at once. Because it takes light about 8 minutes to reach us from our sun, if the sun were to just suddenly vanish right this second, we wouldn't just be sitting in the dark 8 minutes later. We literally wouldn't even feel the gravitational shift on Earth for a full 8 minutes.
Of course, all this understanding didn't just happen overnight. It's been an amazing journey, starting from pure theoretical math that honestly even Einstein himself thought was a bit too weird to exist in the real universe. It wasn't until the 1960s that scientists truly started embracing the reality of these objects, with physicist John Wheeler finally popularizing the whole black hole name in 1967. And incredibly, it took all the way until April of 2019 for the Event Horizon telescope to capture an actual photograph of one, proving the math right once and for all.
Which brings us to Section 2, how black holes form.
Okay, first things first. A black hole is definitely not an empty hole in space at all. It's actually the violently compressed remains of a dying star. The whole mechanical recipe for a black hole relies entirely on a loss of balance. You see, throughout a massive star's life, there's this continuous nuclear fusion pushing outward, perfectly fighting against the inward crush of gravity. But once that star runs out of its hydrogen or helium fuel, that outward force simply stops. The star goes boom in a massive supernova, and gravity just violently crushes whatever is left of the core inward.
But hey, not every star gets an ending that dramatic. Astrophysicist Subramanian Chandrasekhar actually figured out a strict mathematical threshold for this. A star's core has to be more than 1.4 times the mass of our sun to undergo that infinite collapse. So, our own sun? It falls way below this Chandrasekhar limit, meaning it is perfectly safe it will never ever become a black hole.
Just to help visualize the terrifying scale of the compression we're talking about here, though, let's say a star the exact size and mass of our sun did somehow collapse into a black hole. Its entire mass would be squeezed down into a diameter of basically 50 kilometers. Imagine the entire unimaginable weight of the sun fitting into the space of a single city here on Earth. Just wild.
So they basically come in a few different flavors. We have stellar black holes, which are actually super common. We've got theoretical primordial ones, which are supposedly the size of an atom but weigh as much as a mountain. And then we have the supermassive black holes, packing the mass of millions of suns into a space roughly the diameter of our solar system. That one from Interstellar, Gargantua, was a supermassive black hole, just like the real one sitting right at the center of our own galaxy, Sagittarius A star.
Let's take a little tour from the outside in with Section 3, Anatomy of the Abyss.
So as you approach, the very first thing you're going to hit is the accretion disk. Now, Interstellar showed this as a fiery, glowing orange ring.
But the scientific reality? It's a violently spinning ring of gaseous debris getting so severely crushed and heated by gravity that it turns into a fluid-like plasma hotter than 1,000,000 degrees. And because this intense glowing friction emits high-energy X-rays, which are completely outside our visible spectrum, it would actually look closer to a blinding blue. We honestly just color it orange in our graphics to make it easier for human eyes to process.
In that weird shape, where the disk seems to arch over the top and bottom of the black hole, that is a total optical illusion. It's caused by the extreme gravity physically bending the light from the back of the disk right over the top. Combine that with something called the Doppler beaming effect, which just means particles spinning toward us look brighter, and particles spinning away look dimmer, and you get that iconic, distorted, glowing halo.
Plunging even deeper past that disk, we hit the photon sphere. And I love this part. This is an incredibly precise area where gravity perfectly traps light in a continuous, infinite circular orbit. Which literally means if you could somehow stand completely still in the photon sphere and just look straight ahead, the light reflecting off your back would travel in a perfect circle around the black hole right into your eyes. You could theoretically see the back of your own head.
Finally, we cross the definitive boundary in Section 4, inside the event horizon.
Okay, this is it. The absolute point of no return. The definitive boundary. Once you cross this threshold, the gravitational pull becomes so overwhelmingly massive that the escape velocity exceeds the speed of light. And, well, since light is the absolute fastest thing in the universe, if it can escape, absolutely nothing can. Definitely not a human in a spacecraft. Past this line, everything goes permanently, perfectly dark to the outside world.
And right at the very center of all that darkness, that's the singularity. According to Einstein's general theory of relativity, this is a single point where that space-time mesh we talked about earlier bends so deeply that it just stretches infinitely. The known rules of physics completely break down here, and time itself theoretically slows down forever.
So, what actually happens to you if you fall in, like Cooper did? Well, instead of finding a magical 5-dimensional library where you can send ghost messages through time, the harsh scientific reality is that the extreme gravitational forces would just stretch and tear you apart. You'd be completely disintegrated into pieces in mere milliseconds. Yeah, it's a one-way, incredibly destructive ticket.
Now, take a deep breath, because as a comforting takeaway, you really do not need to fear these things like they're universe-devouring vacuum cleaners. Black holes don't just wander around the cosmos sucking everything up. Gravitationally speaking, they function pretty much exactly like our sun. Entire solar systems, planets, and stars safely orbit supermassive black holes right now. As long as you maintain your cosmic social distancing, things just happily orbit them for billions of years.
But here's a crazy thought to leave you with. While we know for a fact you wouldn't survive a physical trip inside, some theoretical physicists suggest that the trapped light might continually reflect internally within the event horizon. Which leaves us wondering, if all that light and information is trapped in there forever, will human science ever figure out a way to peer past the boundary? Will we ever truly discover what hides in that infinite dark? Or are some things just meant to stay perfectly hidden?